All right, welcome back. Um, Chapter 6.4 is titled The Fundamental Theorem of Calculus. And basically what we're going to do is we're just going to talk about some stuff that we've developed over the first three sections. And we're going to talk about their impact on how we solve problems. So the first part of the fundamental theorem of calculus, and the fundamental theorem of calculus is split into two bits. The first part is the antiderivative part. Here's what the antiderivative part of the fundamental theorem says. And I'll point out which things we showed during the last section. But if f is continuous on AB, so thing one, we're starting with a continuous function, then the function capital F of x, which is defined as the integral from a to x of f of t dt, you'll notice that in the last section we referred to this as the antiderivative. And that's fairly important here. That function has a derivative at every point x in the interval AB, and that derivative is equal to the function. So we basically just restated exactly what we found at the end of 6.3, but we're calling this the fundamental theorem of calculus because this is a pretty interesting and important concept that every continuous function is the derivative of some other function. And the other function is defined as the integral from a to x of f of t dt. Every continuous function is the derivative of some other function. That other function being what we call the antiderivative. So let's look at a quick couple example problems. Example 1a, we want to find the derivative with respect to x of the integral from negative pi to x of cosine of t dt. And very simply, that's f of x. Example 1b, find the derivative with respect to x of the integral from 0 to x of 1 over 1 plus t squared dt. And that's just equal to f of x. Notice that it makes no difference at all what that number is. And we talked about y in the previous section, and we'll get back to that again a little bit later. So if you don't remember that, it was video 5 of chapter 6.3. We talked about why that didn't matter. So let's do another quick example using the chain rule. So example 2. We are looking for y is equal to the integral from 1 to x squared of cosine of t dt, and we want to find the derivative of y with respect to x. So here's what we're going to do. We're just going to say let's let u equal to x squared, which means that the derivative of u with respect to x is equal to 2x. And the chain rule says that dy dx then could be written as dy du times du dx. So let's rewrite y as a function of u. Y is equal to the integral from 1 to u of cosine t dt. And the derivative of y with respect to u is just cosine of u, which of course is equal to cosine of x squared. So now, coming over to our chain rule, we've got cosine of x squared times 2x. The derivative of y with respect to x is equal to 2x cosine x squared. Why don't you go ahead, if you're one of my students, go ahead and do exercise 9, and we will come back with some more examples in the next video. Thanks for watching.